Okay, so here's where we were last time. We were talking about vector surface integrals. The point being that we're interested in computing flux as our first application anyway. So flux, we motivated this formula, and then from a sort of a notational standpoint, we motivated this formula. So how do we compute this? When we went through this reasoning last time, with all of this above stuff in mind, we figure, well, hey, if you look at that right there, this points in the direction of the capital N. It's got the magnitude of capital N. It looks like a duck and quacks like a duck. It's a duck. Now, I've confessed in advance that there is a problem with this. We'll talk about what the problem is momentarily. But it's a pretty persuasive and alluring case there. So, okay, so what can we do with our result, though? And we did this last time as well. With this formula, you can compute fluxes from a parameterization. You pull back through the parameterization. And so we looked last time at this vector field on a surface with this equation leading to that parameterization leading to these partial derivatives, et cetera, and you can go through and just plug in, and here's an integral that you could then crank out to compute the flux. Okay. All right, so now confession time. Comes out of the question, in what way does the parameterization matter? And I want to remind you, we've already addressed that for scalar surface integrals. That they're independent of the parameterization. The parameterization doesn't matter for scalar surface integrals. So what about for vector surface integrals? Does the parameterization matter? And mostly not, but there is one way that it matters, and it has to do with orientation. So here's the details. When you have a question given to you, you want to compute a flux. What will come to you as this part of the statement of the question is a surface, but more than that, remember we dwelled on this last time, you have to have an oriented surface. You have to know which of the two possible directions perpendicularly through the surface is the positive one. Which one do you want to consider to be positive flux? And if the fluid's going the other way, it would be negative flux. So for an oriented surface, in other words, for our actual integrand, oriented surface, there is an associated normal vector. On the other hand, when you parameterize, you get various partials that you cross to get the capital N, which you can then normalize to get what we call the parametrized unit normal. And the issue, the little sticky wicket, the thing that made my reasoning on the other page bogus, right, is the fact that it is not at all clear whether these two normal vectors are equal. Right? They're completely unrelated. The surface came with an orientation. Did I think about that when I parameterized the surface? No, not at all. I was just looking at the equation for the surface. That's how we parameterize the surface. I wasn't specifically thinking that I wanted to parameterize in a certain direction, nor is it really immediately clear what that would even mean as I'm parameterizing, as I'm talking about the parameterization itself. So it's a coin flip as to whether the parameterization orientation that you're going to come up with is right or wrong compared to the orientation that is required. That's, again, part of your domain, part of the definition of what you're talking about with flux. So that's the problem. And now to flesh that out a little bit more clearly, a little bit more explicitly in the algebra, here was my asterisk, and I had just said, hey, it looks like a duck, quacks like a duck, so it's a duck. Well, I conflated two things. On the one hand, this N right here, that N, that is what comes from the orientation of the surface. That's the orientation unit normal. That's part of the statement of the question. It's part of the domain. It defines the oriented surface in question. And when I claim that this is equal to that, well, not really. Actually, in it is equal to a unit vector times a magnitude. That part's true. But this direction here is the parametrized unit normal, not necessarily the same as the orientation unit normal. It's a coin flip as to whether those are pointing in the correct direction. So, are these two things here equal? Maybe, maybe not. You have to explicitly look to see if they're pointing in the directions that they should be. Okay. Now that said, what's the cost? I mean, what's the penalty if you guess wrong? What if you have the wrong parameterization? You parameterize upside down, as it were. No problem. Ultimately, your normal vectors are off by a factor of -1. That applies to every term in your integration. Every term in your integration is wrong by a factor of -1. That means your answer is off by a factor of -1. Hey, just throw in an extra factor of -1 and you're good to go. Right? So it's ultimately an easy problem to fix, but is an insidious problem to notice. And it requires, again, the sophisticated understanding of the distinction between the given orientation and the one that you inadvertently create when you parameterize. Okay. By the way, other than that, parameterization doesn't matter. Orientation is the only sticky wicket. Okay, so what I'm going to do now, I'm going to look back at this example. I'm going to change one little micro thing. We're going to look at the same vector field. We're going to look at the same underlying surface. We're going to do morally the same calculation, but with one little tweak, one little twist. Let's see how this goes down, in which I'm going to show you how to deal with this orientation issue and how to make good decisions in relation to it. Okay, so here we go. Same vector field, same surface. It's a graph, gives us the same parameterization, which of course has the same partials, which then give us the same cross product, and thus we have this same capital N vector that we got last time. Now, here's where we have to pause. When you see your capital N vector, this is when you can first see what direction your parameterization is oriented. Before this, you really can't tell. It's very hard to tell looking over here whether this is oriented one way or the other. Really hard to tell. But looking at this parameterized normal vector, we can see. And so here's the way we ask it. So we were supposed to orient downward, right? The question comes as being about downward flux, or said differently, about flux through the downward oriented surface. Did I parameterize downward? Well, nope. Right? You can see right here, my vertical component here is positive. So if anything, you would call this an upward orientation. So I have guessed wrong. I parameterized backwards. I parameterized upside down. However you want to say it, my orientation is wrong. Now, but yeah, question.
And the third coordinate of the parameterized normal vector corresponds to the z-axis?
Yeah, yep, that's right, which is why I relate it to upward versus downward. And you ask a great question. There are some semantical details that I'm going to have to talk about at the bottom of this page, and we'll get to that in a minute. But yes, to your question. Okay, so what do we do about this? How do we avoid this kind of a problem? Wouldn't it have been nice if I could have parameterized the correct way in the first place? How would I go back and fix this parameterization? And frankly, it's very, very hard to see it coming in advance, to parameterize the right way. And it's really not worth going back and fixing it if you inadvertently parameterize the wrong way. If you inadvertently parameterize the wrong way, we know what the answer. The answer is that I'm off by a minus sign, and so you just do the following. Go ahead and keep your upside down parameterization. And then just say, something to the effect of, parameterized upside down, and I'm going to fix it by just inserting a minus sign. Had I not put in the minus sign, I would have gotten the wrong answer by a factor of -1. But with this additional minus sign, I'm going to get the right answer. That makes sense to everybody? It's so easy to fix. So why bother going back with a brand new parameterization? It's just not necessary. Okay. All right. Now there is a subtlety here that I have to address. This is important. Where this ultimately comes out of, y'all heard me say this a million times. I'll probably say it 500,000 more than the rest of the semester. It's not a class about answers. It's a class about reasoning. Right? The answer is, it's, okay, I guess we're kind of interested in the answer, but we want to make sure that your reasoning makes sense. Right? So, it is important, therefore, to put the minus sign in the correct place. It's not good enough if you were to, for example, if you were to leave it off here. Right? And then instead, if you were to put your minus sign only there for the first time, now you actually have two false statements on your work. Let me show you what the two false statements are. The first false statement in what's written here is it seems to be suggesting that this integral and that integral are equal. In other words, it seems to be suggesting that these two things are equal, and they're not. Right? These two things are not equal because the ds points in the direction of the given orientation unit normal. Capital N points in the direction of the parametrized normal that we just got through agreeing are pointing in opposite directions. So if you say in your work that this equals that, it's not. They're different. That statement's wrong. Does that make sense to everybody? It's invalid reasoning because it's a false statement. And then, here's the other false statement. The other false statement is the suggestion that that integral is equal to this. Again, no they're not. This f is that, this n is this, the SDT is that. Everything lines up except there's a minus sign on this one but not on that one. So these things aren't equal either. Now they're canceling sign errors, but two sign errors is still two errors. Right? So again, I know it may seem like this is fussy. It comes off as fussy if you're focused on the numerical result. If you're focused on the reasoning, this is two errors. And so we got to make sure that we don't do that. So where do you insert the minus sign? And then, obviously, of course, you follow it, at all subsequent steps. You put in the minus sign if necessary. Right? If you have parametrized backwards, you insert the minus sign where you're making the switch from a vector whose orientation is defined by the statement of the question, by the initial oriented surface itself, versus the vector whose orientation is defined by the parameterization. That's the distinction here. The reason that this is where the minus sign goes is because these are the vectors that are opposites of each other. Right? This right here is exactly the same as that other blue circled thing. These are not different. There should not be a negative relationship between them. Those are exactly the same. Right? It's the green one versus the blue that are different, and that's why the minus sign has to go here. Is that all cool? Is everybody on board? Okay. All right. So notice it's easy to notice when you have this problem. You just look for the incompatibility. Again, once you've got your capital N vector identified, look for that compatibility or incompatibility. And if it's incompatible, then fix it with a minus sign. It also, you should give some little text to explain. Don't just insert a minus sign with no comment, right? You got to give some justification. You can be very, very terse. You can write something like backwards, whoops, and then draw an arrow to your minus sign. full credit, no problem, right? But I need to see some indication of where that minus n came from. Okay. Alrighty. So moving along, let's talk about the lingo. Here is the surface that we were just looking at. Paraboloid. Approximately. Here's the two orientations that are possible. Now keep in mind an orientation is a choice of normal vector, and there's really only the two choices. There's the ones that I'm highlighting in blue and the ones that I've highlighted in green. That's the only two options of which direction through we want to call positive. You can talk about downward orientation, you can talk about upward orientation, but there is really only the two candidates. So why do I like this language upward? One could make the case that it's a little misleading. For example, there would be a temptation to infer from this that the normal vector is 0, 0, 1. Right? So make sure to understand that is not what this is saying. When we say upward as our orientation, I'm not using a simple word to describe a precise unit normal vector. We're just not. Furthermore, notice this doesn't even make any sense as a normal vector. It's not perpendicular to the surface. Right? So it can't be a normal vector. So I couldn't possibly have meant this. It doesn't even fit the bill. Does that make sense to everybody? Okay, so what do we mean then when we use a word like upward? And what we're doing here is we're not going to be exactly perfect in the description. We just want to remove possible ambiguities. That's all it is. So if you look at these green vectors here, right, this green orientation, notice all of those vectors are pointing at least somewhat upward. Not exactly upward, but they're somewhat upward. They're up-ish, right? Whereas the blue vectors, not a one is in any sense upward. All of the blue vectors have negative z components, so they're just not upward at all. And all of the green vectors are at least somewhat upward. So the word upward unambiguously distinguishes the green option between these two choices. And then likewise, downward. Well, all of these blue vectors are at least somewhat downward. None of those blue vectors are in any sense upward. And the green vectors, none of the green vectors are in any sense downward, right? So again, ambiguity removed. It's perfectly clear. Upward versus downward distinguishes between these two candidates. So this is the language. This is a great choice of language for talking about orientations on that paraboloid. Everybody okay with that? All right. Now you could also, if you want, I suppose, you could say inward versus outward, and I say, well, this is kind of okay. My little quibble with this is the word inward to me suggests that there's an inside, and well, there isn't. Right? Paraboloid is not a closed surface. There is no inside, and so inward, I don't think it's really quite right. But nevertheless, if you say inward, nobody's going to think blue. Right, so I mean, it serves its purpose, but it's a little, suboptimal, I think. I wouldn't call it wrong, but I'd call it suboptimal. All right, now, by comparison, let's consider another surface. Wouldn't it be nice if you could always just choose, one set of, language options that'll apply to every surface? Sadly, no such luck. Take, for example, a sphere. Right, now again, we have two orientation options. There's the one I'm going to highlight in green here. We'll get to language in a second. Then there's the one I'm going to highlight in blue here. Those are my orientation options. And how would I distinguish these? Well, I'll tell you what, if I tried to use the word upward, I'd have a problem. Because some of the green vectors are upward, but some of them are not. And likewise, some of the blue vectors are upward, and some of them are not. So this word here, upward, just doesn't do its job. It does not distinguish between the two possible orientations that I might need to refer to. So this language, and likewise downward, right, equally bad. These words here do not distinguish our orientation, so you cannot use upward versus downward for this surface. Now, keep in mind, this was the preferred terminology for that surface. So different surfaces have different geometry and thus require different language. And in this case, for these surfaces, I think it's pretty clear outward is the perfect description of those green orientation vectors, and inward is the perfect word to describe those blue ones. So here we have some fantastic options. So always tailor your language to the specifics of your surface. It's going to be different for every surface. You got to think through: does this remove all the ambiguities? Does this mean close enough anyway what I need it to mean? And make sure that you remove all the ambiguities. And likewise, when you're interpreting the language, perhaps in a statement of a question or something like that, interpret appropriately to the job at hand. Okay. Here's another example. Y'all can look through. It's an easy read, I think. Okay. Next. Good news. Lucky breaks. The world's full of them. Be on the lookout for them. It's very, very worthwhile. Very often there are integrals that if you were to, put on the blinders and just, plow forward with the algorithm, oh my gosh, it'd be a nightmare. And tons of work, and nobody wants that. I certainly don't. So be on the lookout for slick little fortuitous little bits of good fortune. Okay, so first example, let's consider this sphere right here, sphere of radius 3. Notice centered at the origin. And I've got an orientation given to me. That's cool. And I got a vector field, and I want to compute a flux. So perfectly reasonably phrased question. And the blinders on algorithmic solution here would be to parameterize. Spherical graph parameterization is going to be loaded with trig. That's going to turn this into even more trig. That parameterization would make a ds vector that was full of a lot of trig, which means that this integral that you would end up doing would just be a massive, trig explosion. And I frankly haven't worked it out. I don't know how bad or good that might work out. I'm just not sure. But certainly lots of trig. So the brute force approach, let's call that Plan B. We hope we don't have to go down that road. Here's the good fortune. Here's the thing to be on the lookout for. Spheres centered to the origin have massive symmetries. Just tons of symmetries. And one of them is this fact right here, that the perpendicular to the surface, in this case outward unit normal vector, is always a scalar multiple of the position vector. Now, the justification I'm going to give you for this is just appeal to the picture, right? This is how spheres work. To think about an Earth analog here, sort of an Earth metaphor, upward is always perpendicular to the direction you walk along the surface. Imagine if it was a flat, spherical, part of the world. The direction that you walk and the direction that's straight up are always perpendicular to each other. So, this is a huge payoff because the position vector x is easy to write down. That makes this unit normal vector easy to write down. And combining that with the the vector field we were given in the first place, this is the vector field we need to dot that with. I haven't had to parameterize anything yet, and I've got a kind of a foot in the door. Here is at this point, it's kind of a scalar surface integral, and shoot, maybe I can work out this scalar surface integral in a more convenient way than the original vector surface integral that I actually started with. And in this case, it's extremely convenient because, of course, if you look at this dot product itself, this dot product is just 0, and thus the integral is 0. No trig, no tedious algebra, no cross products, no, lots and lots of trouble. No, just geometric observation, teeniest little bit of algebra, and then victory. Yes?
Can you talk about one-third?
About what? Where come?
Doctor of 1/3.
Oh, yeah, sure. So I'm just thinking about this n vector here, and what do I know about it? I know it's a scalar multiple of the position vector, just because of geometry, but I also know that its magnitude has to be 1. This vector has magnitude 3. The position vector x has magnitude 3 because it's a sphere of radius 3. So if this thing has a magnitude 3, and my little n points in the same direction with magnitude 1, it's got to be 1/3 of that vector. Does that make sense? Yeah. Cool. All right, so sometimes you get lucky with spheres. Oh, yeah, go ahead. Say it one more time.
Did we say that n doesn't have to be a unit vector?
Little n here, at this point, for the convention that we're using in chapter 7 here, little n is a unit vector. Yeah, absolutely. Now, awkwardly and tragically standardly, back in chapter 1 and in a lot of other courses, they use little n, but it doesn't have to be a unit vector there. So, it's just, I don't know, that's the surprisingly common choice. And you just have to remember, if you're talking about flux, if you're making use of little n vector as part of defining a vector surface integral, it's got to be a unit vector. Yeah. Okay. All right, so what's the tip off here? How did I know to try this? How did I know not to parameterize and plug and chug and all of that business? Well, I'm just, spheres are awesome. In particular, spheres centered at the origin. If you've got a sphere centered at the origin, think it through. Consider whether this works, something analogous to this, and see if maybe this might be a payoff. So, in general, if there's something really geometrically convenient about your surface, this is worth a shot. Okay. Now, related example. Well, related to the point I just made. Let's suppose I'm looking at this plane, y = 3. In particular, I'm looking at a certain part of that plane, specifically the part that satisfies this inequality, which is, something like this. And the particulars of that shape are going to end up not mattering, so I'm not going to worry about it very much. But clearly that's just some compact little set inside of the given plane. Okay, and we've got an orientation given to us, and we've got a vector field given to us. We're computing the flux. So now again, you could parameterize. After all, this is a graph. So y equals a function of x and z. You could use the graph parameterization, and you could plug and chug. But look at the easier alternative here now. Because my surface is part of y = 3, I immediately know that my normal vector has got to be perpendicular to that plane, and therefore 0, 1, 0. Again, it says right here positive y direction. Thus, this is the positive 1 right there. So I can write down my unit normal vector. Different argument from the sphere argument. Different geometry, right? But I see that my domain's got something really, really nice about it. It makes it really easy to write down this unit normal. That makes it really easy to start to see how my integral is shaping up down here. And in particular, I see a couple of zeros, and I'm already happy. Everybody with me so far? All right, now what else do I know? Well, whoops. The other thing that I know, again, I'm on this plane, so that means y = 3. That means that every point I'm interested in, y is equal to 3. That means I can plug in y equals 3 everywhere in my vector field. After all, for my entire surface, y is equal to 3. Well, that makes this second component of my vector field 0, which I can insert into there. And game over, we win. The dot product is 0, integral is 0. No more computations required. So you don't have to parameterize and go through that whole song and dance. Again, sometimes just the given geometry can make a problem just unravel right there on the spot. Does that make sense? Everybody's happy? Okay. All right. So again, be on the lookout for this kind of thing. It's surprisingly common that stuff like this comes up. These are manufactured examples, perhaps, but again, I'm channeling my experience as an undergrad who took a lot of classes with a lot of integrals in them. This kind of thing is not a rare circumstance, and it's well worth having your head on a swivel, constantly thinking about your surroundings and your circumstances and looking for these kind of little tricks. Okay, next thing, coordinate surface integrals. Y'all remember coordinate line integrals. And it's kind of a notational thing that ends up looking kind of inconvenient, and it doesn't have a lot of appeal. Right? But then there were a couple of reasons that I pointed out that we needed to be aware of it. So the same thing's going to happen here. I'm going to kind of crank out some notation. In particular, I'm going to take advantage of the fact that we've already made the observation that you can expand out these velocity vectors by coordinates, and you can expand out the cross product by coordinates. You get this oddly suggestive result here, where these coordinates, they look like two-dimensional stretching factors, two-dimensional Jacobian determinants. So where's the two-dimensional change of variables that would have caused this to happen? I would love to spend time talking about that. We just can't. We just don't have the time. You don't need to know, so it doesn't make the cut for spending time on it in class. That said, there's some really interesting ideas in there that will lead to some geometric satisfaction that might even make you believe in coordinate surface integrals a little bit more. If you're curious, come talk to me about it. I'll be happy to talk about it in office hours, or if you want to set aside a time to talk about this, I could probably figure something out. Anyway, that's all I'm going to say about it here. What we're going to do here is consider that the ds vector being capital N times ds dt likewise can be rewritten like that, which I can distribute the scalar differentials there to give me that. And now, what do you think would be a reasonable thing to call this? And again, you kind of channel the two-dimensional change of variables discussion that we had several weeks ago. Partial yz, partial st, times ds dt. It's as if these things cancel. Of course they don't. This is not a fraction. There's no actual cancellation. But it's as if these things cancel. And we've seen this play out previously, and we called this, rightly so, dy dz. And likewise, that dz dx. And this dx dy. So what we've got then is an alternative notation for the ds vector by coordinates. And with that in mind, we're going to do the exact same thing that we did, with line integrals, coordinate line integrals. There's my new formula for the ds vector. Recall that my vector field, of course, is going to have components. I'm going to use the standard-ish, very common choice PQR for whatever reason. And lo and behold, f.ds, I can literally dot it out, and that turns into This right here. And that's just how the dot product expands. And that's my alternative notation then. So in other words, rather than writing a vector surface integral like that, I can instead write it like this. And now, do I want to? Would I choose in Math 219 to opt out of this notation and choose instead to write it like this? I really can't imagine when or why I would do such a thing in this course. It's a lot clunkier to write down. It's pretty unintuitive if you think about it. If we're actually on a surface, a curved surface, angled in some weird way up in space, what is dx dy? This is very counterintuitive. It makes it look like I'm in the xy plane, but I'm not. I'm on a surface. So this is weird and hard to relate to. And there's answers to these questions, and again, we don't have time, and again, we don't need to worry about it. But less intuitive, less compact, hard to see why we'd want to do such a thing. Now, why am I wasting your time with this? And again, there's two reasons. For one thing, it's a cultural point. I want y'all to be aware here and also on, I believe, the next page. I'm remembering, 2 pages down. I want y'all to be aware that there are these things called differential forms, and this thing right here is basically identical to something called an integral of a differential form. Differential forms are very, very powerful. They're ultimately very, very natural. They're a big deal. They're important. They're useful. You can do a lot with them. Well beyond Math 219, so we're not going to actually be able to flesh any of that out. But again, cultural point, I think it's good to know that there's big ideas around that are making certain things happen, and this is the closest glimpse, one of the closest glimpses that we're going to get to seeing differential forms. If you want to see what they really look like, look in Chapter 8. There's some discussion. Even what they do in Chapter 8 is tip of the iceberg. But if you're curious, you can take a look. It's not on the syllabus. You don't have to. So that's one reason. The other reason, because they are natural and powerful, the reality is that this notation is in common use. There are people out there teaching engineering and physics classes who totally dig differential forms. They think it's great, and they use this notation all the time because, and rightly so, they love this notation because they love the differential forms. You're going to see this notation somewhere, here or there, possibly a lot. So I need for y'all to be ready for this notation when you see it, even if I'm not going to use it much, if at all, in this course. It is out there. You are going to see it, and you need to know what to do with it when you see it. So what do you do with it when you see this notation? Well, here's what you do. Recognize that these differentials over here, that's just fancy talk for the ds vector. That's all it is. Right? And then, based on which ones they pair up with, these integrands tell you what is the vector field whose flux, whose vector surface integral this expression represents. So that's what it. You could just look at the structure of the of that coordinate surface integral and reverse engineer the corresponding flux integral. Yeah.
Our bounds are still in S and T, right? So we have to convert it to X1.
All of these integrals are integrals defined on some oriented surface S. I have none of these require parameterization. These are just so how I go about computing these. Well, you have to parameterize, and pull back to some ST plane or something. But none of these are. I'm not addressing that part of it. I'm just talking about these as integrals on S. Is that cool? Yeah. Okay, is everybody comfortable with how to take stuff that looks like this and how to reverse engineer and figure out what the vector field is and how to reconstruct that as just a flux integral? Is everybody comfortable? Okay. Cool. All right. Okay, let's talk about symmetry theorems. I have good news and bad news. We'll start with the good news. For scalar surface integrals, we have a symmetry theorem. You're going to notice that these comments here are all laid out on the page exactly the same way as all of our previous odd symmetry theorems. Again, that's very deliberate. I want to emphasize how much they are just the same idea applied in different circumstances. So, just to flesh it out, if you have an odd integrand and a symmetric domain, your integral is 0. And now a reminder, word of warning, you do have to have both conditions satisfied, and you also have to make sure that you are using the same plane for both of those conditions. But that said, with the conditions satisfied, integral is 0. You don't have to parameterize or take any antiderivatives or find any bounds. It's just boom. Awesome. Everybody okay with that? Seem kind of believable? That's good news. Okay, so I'm a big fan. I wanted to point out, somebody asked me in office hours today about it was one of the homework exercises, and I have conveniently forgotten which one, because I think it's a good exercise for y'all to be on the lookout for it anyway. But, so without knowing which one, I do want you to know that at least one integral on this week's homework is a scalar surface integral that is equal to 0 by way of this symmetry argument. So be on the lookout. That's going to save you loads of trouble. Is that cool? Okay. All right. Now, here's the bad news. Good news, bad news. The bad news is this is very specifically, notice I have it underlined, only for scalar surface integrals. If you have a vector surface integral, no luck. There is no odd symmetry theorem for vector surface integrals. It does not work. It doesn't make any sense. It's just not true. It's garbage. So now I want to give you some sense for why that is. Reminder, a vector surface integral is something that looks like that, which I can rewrite like that. Let's focus on this phrasing of it, and let's look at what I like to call the differential here, the ds vector. Looking at the pieces of the ds vector. Now the ds scalar, you see a symmetry thing here, right? If I were to chop up this surface, appropriately, that little piece of surface area there, this little piece of surface area here, you have about the same size, right? You could imagine the same, and this is looking good, and you can see how they pair up, and they might even cancel eventually, blah, blah, blah. But here's the problem, where it all crashes and burns, is when you look at the normal vectors. There's one of the normal vectors. Here's the other normal vector. Are those normal vectors the same? Nope. Right? I mean, that's just because of the shape of the surface. This isn't even an obscure, manufactured, rare kind of a surface. This is easy. The surface kind of bends a little bit, right? It looks like a pretty little potato chip. This is a very routine, normal little surface, and clearly normal vectors are just not the same. So, no symmetry argument for vector surface integrals. Does that make sense to everybody? Is that a hand? Yeah.
What if you, maybe wrong here, what if you broke it up coordinate-wise? What if you could get the x components of either...
Yeah. Well, okay, sure. So one thing you can do, right? You can certainly, if I can erase all my junk here, you can certainly take your vector surface integral, right? And you can rewrite the vector surface integral like this. And if you can find an equation for your unit normal vector, and if you can thereby actually compute this integrand, which of course is not the same as this integrand, right? Because one in blue doesn't incorporate the unit normal. The one in green does. Once you've computed out this dot product, you have a scalar surface integral. And you can use the scalar surface integral odd symmetry theorem that we just talked about. That's perfectly fine.
Okay.
Absolutely. But if you want to make an argument based on whether or not the vector field F is odd or not, that was nothing. There's no theorem there.
Okay.
Yeah. That's a good thought. I like that. Anybody else? Okay. All right. All right, that's good enough. Oh, so so I did want to say though, I always feel it necessary to make a big deal out of this. That for vector surface integrals, there is no odd symmetry theorem because symmetry is delicate and dangerous. And I love it, and I'm a big fan, and I use it all the time. But it is delicate and dangerous because if anything goes wrong, then there is no symmetry argument. And if you make a symmetry argument that doesn't work when there was no symmetry argument to be made to work, then nothing on the page is relevant to the solution to the question. And I as much as I love giving partial credit, and again, I'm always doing my best trying to find excuses to give students partial credit, if nothing on the page is relevant to an actual solution, there's nothing I can give partial credit for. So please don't try to make an odd symmetry argument for vector surface integrals. It doesn't work. It doesn't make any sense, and all your work is wrong at that point. So it's very, very dangerous. I make a big deal out of it to try to minimize the likelihood of a student stepping on that landmine. Okay. All right. Last thing we're going to talk about today. We won't finish this today. This takes several more minutes than the 3 we have remaining. But I want to talk about analogies between vector surface integrals and vector line integrals. They don't seem like they ought to have much in common. After all, vector line integrals have to do with work. Vector surface integrals have to do with flux. Flux and work are completely different physical concepts. Why would there be any relationship between them? There's no physical motivation that I'm aware of for why these should have something in common with each other. So, turns out though, there are lots of analogies, lots of comparisons. They have a lot in common with each other. And ultimately the reason why is because they are ultimately both the same thing. And I've already made this observation. They're both integrals of differential forms. Just different kinds of differential forms. Right? But they are integrals of differential forms. So the reason I tell you this is because the fact that they have something in common, even if we don't actually know what that is, just knowing that there is a connection and there is a unification between these concepts suggests that they might have more sort of in common than they would expect in terms of how they lay out on the page. So, let's see. So what I will... Okay, real quick. This is what a parametrization of a curve looks like. Apologies for the fact that my curve here is sitting here physically below the t-axis. Normally I do my parameterizations left to right, but I'm trying to squeeze all this onto one page, and I wanted to have the left side for line integrals and the right side for flux integrals, and it just doesn't fit if I don't kind of angle them a little bit. So sorry about that. Anyway, this is the picture. Various players involved with vector line integrals indicated on the diagram. Various established relationships noted. Right? Likewise over here, this is a parametrization of a surface. The various players indicated on the diagram. Their various relationships. All of this is old news. Nothing on this page is new. All of this has been written down previously. And with this background, with this context, kind of set up, what we're going to see next time is some very strong relationships between, for example, the velocity vector of the parametrization of a curve, which you'll see there and there in the algebra, versus the capital N vector, which is a kind of a derivative of the parameterization of a surface, showing up kind of there and there. And notice they fit in analogous places in the algebra. And what we're going to find is that all of the players in these stories partner up with something on the other side and fit in analogous places in the equations. And so I think it's really valuable to notice when there is such an extremely strong pattern of comparison and analogy. I think it's really important to notice it. And we'll go through the rest of these details next time. So we'll draw a line. Oh, I'm going to draw the line right here. How about for today? Picking up here on Friday. Y'all have a good rest of your Wednesday. See you later. Don't forget to make sure I get you marked down for a